Could the planet be whispering a warning, or are we listening for patterns where only coincidence reigns? In the space of a single week, the solid Earth has staged a striking set of performances. A 6.6 magnitude earthquake offshore Western Sumatra and a 6.0 magnitude quake beneath central Alaska, while 5 major volcanic centers, Mount Semeru, Kīlauea, Fuego, Popocatépetl, and Hayli Gubbi in Ethiopia, have all shown renewed eruptive behavior. Why would such geographically disparate systems register increased activity at once? Do the pulses of magma and the slips on faults share a deeper mechanical connection, or are they independent outlets of a restless but uncoordinated planet? Is the lack of very large, magnitude 7 or greater earthquakes in recent weeks a sign that major plate boundaries are locked and storing elastic strain, or simply a statistical lull? These are not idle curiosities. They probe the fundamental physics of how stress accumulates, migrates, and finds release in the lithosphere and asthenosphere. On the morning of November 27th, 2 earthquakes of note were catalogued by global seismic networks. The first, a 6.6 magnitude event, had an epicenter located approximately 45 kilometers west-northwest of Semeru, Indonesia, at coordinates 2.69, 2 degrees north, 96.027 degrees east, and occurred at a focal depth of about 25.4 kilometers, roughly 15.8 miles. The second struck later that same day in Alaska, a 6.0 magnitude event with an epicenter roughly 12 kilometers west-northwest of Susitna, at 61.57 degrees north, 150.751 degrees west, and a focal depth of about 69.4 kilometers, around 43.1 miles. These 2 earthquakes are real and recent. They are geophysical anchors for a discussion about mechanisms rather than theatrical coincidences. Mechanically, the 2 quakes could not be more instructive because they exemplify distinct tectonic settings and slip processes. The Indonesian event lies on the Sunda subduction margin, where the Indo-Australian plate converges with and descends beneath the Eurasian plate. Subduction interfaces are capable of hosting both shallow megathrust ruptures and shallower crustal earthquakes, and they host the deep, volatile, rich magmatic systems that build the archipelago's stratovolcanoes. A 6.6 magnitude shallow event in such a setting typically represents rupture on or near the plate interface or on adjacent crustal faults. It relieves some localized elastic strain, but unless it propagates into a much larger rupture, leaves the vast potential energy stored along the locked portions of the megathrust largely intact. By contrast, the Alaska event is a classic intraslab earthquake. Its focal depth of roughly 69.4 kilometers places it well within the descending oceanic plate as it bends into the mantle beneath North America. Intraslab quakes arise because the slab experiences complex bending, unbending, and hydration-induced phase changes as it is forced downward. These processes induce heterogeneous stress fields inside the slab and can trigger normal or reverse faulting within the plate itself. Energy released by intraslab events is significant at depth, but is often attenuated by the time seismic waves reach the surface, meaning such earthquakes can be widely felt, yet cause relatively modest surface deformation. Importantly, an intraslab slip does not necessarily relieve stress on the megathrust interface directly. Its immediate mechanical consequence is internal reorganization of stresses within the subducting plate. Understanding whether these slips and the concurrent volcanic activity are causally linked requires careful passing of stress transfer mechanisms. Two primary modes of interaction are recognized by geophysicists. The first is static Coulomb stress transfer. When a fault slips, it changes the static stress field in the surrounding crust and upper mantle, promoting failure on some neighbouring faults while inhibiting it on others. Static stress changes drop off quickly with distance, and while they can importantly advance or delay failure on adjacent segments of the same fault system, their magnitude across ocean basin scales is typically negligible. The second mode is dynamic triggering. Seismic waves radiating from a quake can transiently modulate pore pressures and the stability of nearby faults or magmatic systems, sometimes provoking swarms, volcanic unrest, or eruptions at distances of thousands of kilometers. Dynamic triggering is real and documented, but it is probabilistic and rarely deterministic. It depends on the amplitude and frequency content of the waves, the pre-existing state of stress and fluid saturation, and the resonance of local structures. Beyond these two, there is a broader system-level perspective. Tectonic plates do not act as independent beads on a string, but as parts of an interconnected mechanical continuum. Long-term coupling on megathrusts accumulates elastic strain over decades to centuries, and that stored energy is episodically released in large earthquakes. If in the recent month-long window there has been an absence of earthquakes of magnitude 7 or larger, then some of the usual outlets for large energy release have not occurred. A prolonged scarcity of very large events can mean one of two things. Either the global rate of strain accumulation has been temporarily balanced by smaller releases, or major segments of plate boundaries are remaining locked and accumulating excess elastic energy. The latter is a condition that raises the probability, not certainty, of an infrequent but very large rupture when those locked patches finally fail. Volcanic systems, meanwhile, express lithospheric and mantle processes in a different currency: mass and heat transfer. The eruption of Kīlauea, driven by a deep mantle plume beneath the Hawaiian Islands, is the most straightforward example of magmatism decoupled from plate-edge subduction mechanics. Kīlauea's basaltic magma is relatively low in viscosity and volatiles compared with the andesitic-dacitic compositions of many subduction-zone volcanoes, which allows effusive eruptions and high lava fountains without necessarily involving large pressure build-up of the sort that triggers explosive pyroclastic behavior. Episodes of high lava output and lava fountaining at Kīlauea indicate robust mantle-to-surface throughput and record fluxes of melt from the plume conduit system. Because the source is a mantle upwelling that is largely independent of plate locking elsewhere, Kīlauea's activity does not straightforwardly signal an imminent megathrust failure. Subduction-related volcanoes such as Mount Semeru, Fuego and Popocatépetl tell a more complicated story. The magma beneath such edifices is generated by flux melting in the mantle wedge above the subducting slab, where water and other volatiles introduced by the descending plate lower the melting point of peridotite. Magmas rise buoyantly through complex, often polybaric plumbing systems, evolving by crystallization and volatile exsolution. Eruptions therefore reflect changes in the supply rate of magma, the open, closed state of volcanic conduits, and internal pressurization dynamics driven by gas exsolution and crystallization. A subduction zone volcano erupting in temporal proximity to a regional earthquake could be responding to transient stress perturbations that alter the pressure in its shallow magma reservoir or the permeability of surrounding rock. Yet many eruptions occur in the absence of any nearby seismic trigger simply because magma supply and chamber overpressure reached critical thresholds. Hayli Gubbi in the East African Rift introduces a tectonic motif distinct from the Pacific Rim: continental rifting. The East African Rift is an extensional environment in which continental lithosphere is being pulled apart, generating decompression, melting in the upwelling asthenosphere, and creating fissure-fed shield and rift volcanism. A volcano that had been quiescent for many thousands of years, suddenly erupting within such a rift, indicates either a change in melt supply or a fracturing event that opened pathways for magma ascent. In rift systems, faulting and magmatism are tightly coupled. Normal faulting increases permeability and can localize magma migration, while dike intrusion can promote faulting by thermally and mechanically weakening the crust. The awakening of a long dormant rift vent speaks to evolving extensional strain partitioning in that locale, but it does not require or imply stress changes on distant subduction zones. When investigators talk of a planetary pressure cooker, they are using a metaphor to highlight a real physical concern. If large, normally stress-discharging faults remain locked for longer than expected, the global distribution of stored elastic energy becomes anomalous. In such a scenario, the system seeks alternative avenues for dissipation. Magmatism is one such avenue. Converting mechanical strain into heat and mass transport via melt ascent is a form of geodynamic compensation. But the conversion efficiency is messy and limited. A magnitude 6 earthquake releases only a fraction of the strain energy that a magnitude 7 earthquake would release. Orders of magnitude differences in seismic moment mean that many moderate events cannot substitute for a missing great rupture. Moreover, the spatial distribution of magma release is uneven and localized. An influx of magma beneath a volcano 1,000 kilometers from a locked megathrust will not appreciably alter the stress budget on that megathrust. Another process relevant to the discussion is aseismic slip and slow slip events on subduction interfaces. These phenomena can release strain gradually without generating large seismic waves, and in doing so they can alter the stress state of neighbouring locked patches, sometimes advancing or delaying the timing of seismic failure. Slow slip events can also be accompanied by tremor and by transient changes in pore pressure. Detecting these subtle transients requires dense geodetic networks and careful time series analysis. Where such instrumentation exists, slow slip has been observed to modulate seismic hazard. Where it does not, the absence of observed magnitude 7 earthquakes could partly reflect redistribution of strain into aseismic modes. The question of what happens if the apparent global quiet in very large earthquakes ends abruptly is a sober one. A megathrust rupture behaves according to fracture mechanics. Growth of a crack proceeds when stress intensity at the rupture tip exceeds the fracture toughness of the fault zone, modulated by frictional properties and the presence of fluids. The size of a rupture depends on the length and width of fault that slips and the average amount of slip. If a large, long, locked segment of a subduction interface breaks in a single event, the seismic moment will be very large and the surface and near-field deformation dramatic. The physical triggers for such a rupture can be incremental. Static stress brought above threshold by slip on a neighbouring segment, increased pore pressure reducing effective normal stress, or a direct perturbation from magma-induced fault weakening in rare cases. But none of these triggers are deterministic. They change probabilities rather than certainties. It is important analytically to separate temporally coincident phenomena from causal sequences. The contemporaneous occurrence of multiple eruptions and moderate earthquakes could be a manifestation of an Earth system in heightened activity, a familiar state for the planet. Alternatively, it could be a symptom of stress redistribution that has favoured magmatic escape over seismic rupture in certain regions at this time. Determining which requires integrating seismic catalogues, geodetic strain rates, models of Coulomb stress changes, magma chamber inflation and deflation histories, and petrological data that constrain melt fluxes. Geochemically, for example, sudden changes in erupted magma composition can indicate a newly arrived batch of melt from depth, or the injection of volatile rich magma that dramatically increases chamber overpressure. Such signals would support the hypothesis of enhanced mantle to crust throughput. Geodetically, transient uplift or subsidence preceding or following eruptions can reveal mass transfer and redistribution of stresses. In practical scientific terms, the recent events call for 3 lines of focused inquiry. First, precise geodetic monitoring of the most seismically coupled plate boundaries should be used to assess whether locked patches are indeed accumulating anomalously high strain. Second, seismic waveform analysis should test for dynamic triggering signatures, for instance, whether the seismic radiation from one event produced measurable perturbations in distant volcanic tremor or microseismicity. Third, petrological and geochemical studies of erupted materials from each volcanic center can determine whether melt supply rates or volatile contents changed in ways consistent with the system-wide modulation of magmatism. The verdict on whether we face a pending megathrust is not binary. Science deals in probabilities and evolving evidence. The lack of magnitude 7 or greater earthquakes in recent weeks is noteworthy and merits elevated vigilance because the distribution of elastic strain is a primary control on seismic hazard. But the presence of multiple eruptive events spanning subduction zones, hotspots and rifts shows the range of natural mechanisms by which Earth relieves energy. Some of these mechanisms are coupled, many are independent. The planet's lithosphere is a complex, heterogeneous medium in which stress, temperature, composition, and fluid content conspire to produce local responses that may sometimes reverberate at a distance. For the scientific community, the immediate tasks are empirical and methodological. Continue to refine high-resolution models of stress transfer, maintain and densify geodetic and seismic networks where possible, and coordinate geochemical sampling to track magma sources and fluxes. For theoreticians, this episode is an invitation to improve integrated models that combine elastic and viscoelastic deformation, fluid pressures, and magma dynamics to assess how strain may partition into seismic versus magmatic release on global scales. In a nutshell, the recent cluster of activity, 2 significant earthquakes of 6.6 and 6.0 magnitude and multiple volcanic eruptions across very different tectonic regimes, does not in itself prove a pending global catastrophe. What it does do is illuminate the multiple mechanical pathways through which the planet vents energy. It highlights that locked faults, intraslab stresses, decompression melting in rifts, flux melting in subduction zones, and deep mantle plume dynamics are all active players in Earth's energy budget. Whether the current pattern is a transient burst or a symptom of an accumulating imbalance will only become clear as more data, more analyses, and more time resolve the signals beneath our feet. Until then, the geophysical questions remain sharp. Which faults are truly locked? How efficiently can magma act as a pressure release in different tectonic contexts? And how does transient stress from one part of the planet modulate failure elsewhere? Those questions, answered with measurements and models rather than metaphors, will determine how we understand this most recent chapter in the ever-unfolding tectonic narrative. If you enjoyed this deep dive, make sure to like, share and subscribe. And do not forget to tap that hype icon so you never miss a breakthrough update. Huge thanks to Amalhei MC28, my very first channel member. Your support means everything. And if you want access to exclusive, members-only videos and early releases, join the channel now and be part of the community that gets the inside scoop before anyone else. Let's keep pushing the frontier together.